In this video I want to talk about a new kind of force that we haven't talked about yet. And it's a category of forces. It's not one particular force. But it's related to what's called Hooke's law. So there are a group of forces that obey Hooke's law. Now the prototype for this, and what I'll start talking about, is when an object is attached to a spring. So here is an object attached to a spring, and the spring is fixed at one end, right? And so let's also assume that this is frictionless, this surface. We don't want to bring friction in yet. Okay, so this is like ice. This is super smooth ice. So this object can kind of go back and forth, right? And the spring will push it or pull it depending on where it is. Let me flesh that out. So let's define an x-axis. And let's say that where the object is when it's sort of at rest, when it's in equilibrium, is 0. So at this point, the spring is not stretched out, it's not squeezed in or compressed, and so the object will just sit there, right? Because the spring really isn't doing anything. Okay, now if we were to push this object in, so now the spring will be more compressed, right? Then the spring will be pushing back. The spring force will be pushing this way. Or if we pull the object out this way, then the spring will get stretched out. And the object out here, the spring will be pulling it back. Okay. And I think it's believable that looking at this picture, the more we pull this object out, the stronger the force will be that's trying to bring it back, right? And so sometimes this force is called a restoring force because it kind of wants to restore it to where it is, quote unquote, supposed to be. A restoring force. So when it's out here, there's a force pulling it back, or when it's in here, there's a force pushing it back there. And the more it gets pushed in, the more it is pushing back on it. If you started here and if you just moved it a little bit, like a centimeter to the right, yes, there will be a force trying to pull it back, but it won't be a very strong force. But when you pull it out, 10 centimeters, 20 centimeters, now the force will be stronger. And so the force is, well, I'm just repeating myself, the force is stronger the further away you are from the equilibrium point. And what we find in practice is that these forces tend to be very close, and in some cases almost exactly proportional to how far away you pull them. So if on my x-axis this is 0, and so this is, if I pull it all the way out to some positive x, then the force is going to be a constant multiple of that x. And this is called Hooke's law. So the force from the spring is your x value, wherever you are, times a constant, which we'll call k. Now the negative is just an indication that it's in the opposite direction. So if you pull it to the right, the force is to the left. If you push it to the left, the force will be to the right. Okay, so that's what the negative is doing there. The k is just a constant of proportionality. And again, the x is indicating that the more x is, the further you stretch it, the more force there will be. Now it could have been x squared, x cubed, square root of x, but in practice we find that it usually is just x. So not only is it a restoring force, it's a linear restoring force, right? This is a linear function of x. So Hooke's law is a linear restoring force. Springs are, as I said before, the prototype of a linear restoring force, or a Hooke's law type force. By the way, this is named after Robert Hooke, who was a scientist back in the 1600s. Now the K is called the force constant or the spring constant if it really is a spring. We just call it a spring constant. So every spring comes with a K, and that's sort of a measure of how tight that spring is. So you can imagine a really tight, hard to stretch spring that would have a really high K, or you can imagine a very low K would be like a real loose spring, like a slinky, that kind of a thing. So it measures the tightness of the spring. If you notice, it takes meters and gives you newtons when you multiply it. So it is in newtons per meter. That is the unit for the force constant. Okay. A quick example that shows this. An object is attached to a spring with a K of 3,200 newtons per meter. So that's a property of the spring. Now a person pushes the object inward with a force of 2,000 newtons. By how much does the spring compress before the person can't move it anymore? All right, so here's the situation. Before we push it in, so now we push it in. And let's say we can push it as far as here. Okay. So at that point we can't push it anymore. And that is because we're pushing in with our force, which I'll just call F, but now the spring is pushing back. And at this point they're equal, right? Because the more we push in, the stronger that Fs is going to get. So at some point they're equal, and so we can't go any further, and the object stops accelerating, it stops moving. So I've pretty much drawn my free body diagram right here. Here's the object, F going this way, Fs going this way. This is all happening in one dimension. I only need one axis, one number line. This can be my positive side, this can be my negative side. So by how much does the spring compress, right? So what is this X right here? Okay, so Newton's second law, F equals ma. Fs is in the positive direction, minus F, which is our force that we're pushing this way, right, equals ma, but we're talking about the point where there is no acceleration, so that is 0. So Fs equals F, right? Again, as I've already said, these two forces are counterbalancing each other, so they're equal in magnitude. Now I know I have the Hooke's law formula for the spring force, which is minus kx. And so x equals F over negative k. So that's going to be my answer. That's the location of the object when we can't push anymore. So that is 2,000 newtons divided by negative 3,200 newtons per meter. Notice the newtons will cancel, and the answer will be in meters. And this gives us an answer of, and sorry, I'm putting it in my calculator now. I did not figure this out ahead of time. Negative 0.625 meters. So 0.625 meters inward, right? 62.5 centimeters is the answer. Okay, so that's an example of using spring force to figure something out. This was actually a type 2 problem, right? This is where we knew the acceleration, and we weren't solving for a force, but we were solving for a piece that goes into the force. So same idea. All right. Now just a few things I want to discuss when it comes to forces that obey Hooke's law. They're not always exact. I'm not saying that everything is exactly Hooke's law, but it is a good approximation for a lot of things. Definitely springs, and we often will talk about springs as a stand-in for anything that's a Hooke's law. any material, actually, any solid material that has some stiffness to it, but of course anything can be bent at least a little bit. So if you bend something, stretch something, compress it, deform it in some way, and if you don't do it too much so you actually permanently bend it or break it, it'll go back. And in fact, it'll vibrate a little bit, like or I should say, it'll oscillate. So it'll bend back, but it'll go a little bit past, and then it'll come back. And that force that is pushing it back to the way it originally was is a Hooke's law force. A pendulum is another example, and we'll talk about pendulums later. But and this is a slightly different situation, but if you sort of have an object attached to a string, and the string is attached up at the top, and you let go, then there's a force that's going to pull it back this way. Of course, it'll overshoot, but then as it overshoots, there'll be a force going back the other way that'll try to bring it back, and it'll go back and forth. And that actually, so I already said Hooke's law is a good approximation to the real force, but it's not always exact. And I think I mentioned this already. For springs or deformed materials, there is a point if you go too far, if you bend it, if you compress it, whatever, too much, you'll break the actual material. There'll be a molecular tear or something like that, and you'll lose the integrity of the material and it won't go back. So that'll break things. When Hooke's law is the only force acting on an object, what will happen? Well, notice that it's not a constant force. I want to be very clear about this. If 0 is here and we stretch this object out and we let it go, so once we let it go, the only thing that is acting is the Hooke's law force. Well, so there's going to be a force pushing this way, but that force is based on how far it is. But if this thing if this thing starts accelerating this way, then a moment later it's going to be a little bit closer, which means the x will be smaller, which means the f will be smaller, right? Because again, f is proportional to the x. So now the force is different. So now the acceleration is different, but it's probably still moving, right? So we kind of have this interplay between x, which determines f, which of course through F equals ma determines the acceleration, and then if it's accelerating, that'll change the x, which changes the f, which changes the a, which changes the x. So they're all changing simultaneously in a way that Newton's second law is always holding and Hooke's law is always holding, but they're all changing together. So this is all to say that it is not a constant force. That's the main thing I wanted to say. So we love when we have constant forces, because then we would have constant acceleration, and then we get to see how the object will move using our constant acceleration for equations, right? But I want to be very clear that Hooke's law is, when there's a Hooke's law force involved, we do not have a constant force. We do not have constant acceleration. You can work it out. So there is a more complicated differential equation that Newton's law gives. I'm not going to get into that right here. But what will happen is, and we talked about this very briefly, we get simple harmonic motion. So that was the motion where the thing goes back and forth and back and forth. Definitely not constant acceleration, but yeah, it is a very common special type of motion that we will examine in detail in a later chapter. And so I just want to sort of put this into your brain at this point. Hooke's law, if it's the only force anyway, will lead to simple harmonic motion. So yeah, if we let go of this object, this thing will just bob back and forth forever in simple harmonic motion. Okay, so we'll examine that. We'll talk about what that means exactly and quantify it a little bit later.